Today we are going to discuss about Phasor algebra. Phasor representation. As we know, AC quantity has magnitude and direction both. When there is a AC quantity, it can be represented in space and time. This is representation of AC quantity in space and time as and angle. Magnitude and angle is known as Phasor representation. Here let me consider at an angle of theta 1 the magnitude of the quantity was this one, whereas at angle theta 2 the magnitude of the quantity was this one. Let it is V1, it is V2. At this 90 degree the magnitude of the quantity is at 90 degree, the magnitude of the quantity is maximum for this sine function, because here we consider this is sine function. And for this phasor OA phasor is defined by, this is OA phasor, this is O OB, this is OB corresponding to this quantity, this quantity is OB, and here it is up to this point it is OB, and at this point it is OD, and this is OC. Now this quantity as a function of this sine of theta can be analyzed as, this is OA sine of theta 1 for this angle theta 1, when this quantity is OC will be sine of theta 2. That this quantity is resolved along y-axis and x-axis. If this is taken as sine of function and we are knowing the magnitude as maximum is V, and this quantity can be represented as Vm sine theta 1, and similarly OC can be represented as Vm sine of theta 2. This is the phase representation of the quantity with respect to reference, and this is taken as reference. Corresponding to this reference, this one quantity is at theta 1, the another quantity is at theta 2. Now similarly, when we are considering the phase and phase angle with respect to this reference, if this quantity start before this reference by an angle of theta or after this reference by an angle of theta, then we can say there is phase lead or lag. And here we consider this quantity start after this reference angle by an angle of theta, there is a lag because it's starting after the reference. The phase of AC quantity is the graphical representation of sinusoidal since it last passes through 0 value with respect to the reference. This is the reference. It passes from, this is the phase, uh, and it passes from it starts from 0 since it pass with respect to the reference, the last passes to 0, and hence we can say this is the phase with respect to reference, and by an angle it is different, that angle is known as phase angle. Now the phase difference. Suppose we are, instead of having one phasor or one quantity, we are having two quantity. One quantity is A, another quantity is B. A quantity is having magnitude V m1 sin omega t, another B quantity is having magnitude V m2 sin omega t minus theta. Here theta means if this quantity A is starting with respect to reference, starting from the reference, whereas the B quantity will start by an angle of theta after this reference, and that is why it is minus. If it was starting before this reference, then the same can be written as plus theta. Now here A quantity is Vm1 sin omega t and B quantity is Vm2 sin omega t. If both the quantities are starting with respect to reference, it means there is no phase between the phase difference between quantity A and B. Now these are the two quantities, same A and B, whereas one quantity is having omega t, another quantity is having omega t minus pi. Pi here means 180 degree. It means if one phase is start with this path, the another phase or another quantity will start from this in this way, and hence these two quantities are just opposite to each other, and that is known as phase difference of 180 degree, and simply means two quantities are varying in opposite to each other in space and time. Now This is the representation of quantity for phase lead or phase lag. Suppose we are having a and B quantity. A quantity start 0 with respect to reference. This is the reference line, and B quantity start after an angle of theta. And in that way, this waveform can be represented in this phasor using phasors. And phasor here is OA and OB. If it is OA and OB, and one phasor is along the reference because it starts from the reference, whereas the another phasor is at an angle of theta because it start after angle theta with respect to reference, and hence it is represented by an angle of displaced by an angle of theta with respect to reference. Why it is taken downward? Because it start after, and hence it lacks the quantity A. Whereas in second case, in second this quantity can also be represented as this one. If we are taking B along the reference axis, it simply means your A quantity. If we are taking B along the reference axis, suppose this is the reference B, and then this is A quantity. This is A, this is B. This reference shifted to B. In that case, then B will be taken as along this reference axis, and A will start before the reference axis, and hence the angle will be taken as theta. And it is taken as anti-clockwise. Anti-clockwise, when it is taken as clockwise, it means A is anti-clockwise, then it means A is leading the phase or quantity B by an angle of theta. Whereas in second figure, these A and B are interchanged. Here we consider B is along the reference, whereas A start after this reference by an angle of theta. Then this will be the phasor for B will start with reference and A start after B. This is B. B start with reference and A start after the this reference, and hence we can say this A is lagging the quantity B by an angle of theta. Whereas this is the case when A is taken as along A is taken as, now this is the case when reference is taken over here along this A, then A will be taken as along the reference, whereas B is before this reference by having the displacement or phase of angle theta, and hence it will be leading by an angle of theta. Here we can say A leads the B leads the A quantity by an angle of theta, or A lags the B quantity by an angle of theta. This is the case when A leads the quantity B by an angle of theta. This is A leads the quantity by an angle of theta to B, whereas A lags the quantity B by an angle of theta. Now, from this graphical representation, if suppose we are having the two quantity as one it is voltage, another it is current, and in this case current and voltage may be having some angle of plus minus with respect to theta and with respect to reference, and in case of plus minus with respect to reference, and in that case if it is at theta 1, if it is at theta 2, then taking the reference, the first is taking considering V is plus theta, whereas I is minus theta, theta plus theta 1 minus theta 2. This is reference. With respect to reference, V will be somewhere here, V angle of theta 1 by an angle of theta 1, whereas I is at minus, this will be minus of theta 2. The angle between these two quantity I and V will be theta 1 plus theta 2. Two quantity A and B are said to be in phase lead or lag when they are not passing through zero value at the same time. Quantity A leads the quantity B. In figure 5, it can also be defined as quantity B lags the quantity A by an angle of theta. Similarly, the other two phasors can also considered. In figure 6, the phasor represents two quantity with respect to the reference. Here it is the reference, when reference along reference, if a quantity is taken along reference, or b quantity is taken along reference. Now, considering the notation, complex notation, since we know there are two quantity, one quantity, independent quantity. Earlier we considered two independent quantity, but now if we are considering there is one quantity with respect to reference having two axes. One it is real axis, another it is imaginary axis. When this quantity is resolved along real axis and imaginary axis, this real component can be analyzed differently, this imaginary component can also be analyzed differently, and real and imaginary components are displaced by an angle of 90 degree. Here the angle is theta. Resolving this component along x-axis and y-axis, we can represent this quantity as x is equal to x is equal to x cos of theta, that is plus, this is simply, it can be represented as x sin of theta, and this is square of the quantity. We can calculate the value of x. Now, instead of writing this function as x square cos of theta square plus x of sine of theta square, it can be simply represented as OA plus or minus JOB. And here plus here means this quantity uh, is 90 degree ahead of the quantity B, and if negative here means this imaginary component is 90 degree behind the quantity A in space, and hence this is considering the real and imaginary component. OX can be represented as OA plus JOB or OA minus JOB, and here OX is nothing but taken as magnitude as x. OA will be that is x cos of theta, and B is nothing but x sine of theta, and these quantities are same. When these two parameters are represented in this way, this is known as rectangular form or symbolic form of AC quantity, representation of AC quantity. Now, similarly, this quantity can also be represented in trigonometrical form. In case of trigonometrical form, OX can be written as OX into a cos of theta plus minus J sin of theta, as we have considered in case of resolving the component along x-axis and y-axis. Whereas in polar form, this quantity can be represented as a magnitude and plus minus of angle theta. Theta will remain same as we have considered earlier. When we want to expand this quantity, then we can simply write OX under bracket cos of theta. If here it is plus, then it will be taken as plus sine of theta, and if it is minus over here, then OX cos of theta minus J sine of theta. This is the polar form, and this polar form is now converted into trigonometrical form. Putting the value of cos of theta and sine of theta and then multiplying by OX, this quantity will become in the form of real and imaginary, and that will be same as that of this rectangular form, and hence this trigonometrical form, polar form, and rectangular form are nothing but the different representation of AC quantity in complex system. The last one is the exponential function. Exponential function is written as OX e to exponential of plus minus j theta. It also simply means OX cos of, if it is plus here, the cos of theta plus j sine of theta, or if it is minus here, then its sign will be taken as minus, rest will remain same. This is exponential function or exponential form of AC quantity. Now, what is the significance of these different forms, rectangular, trigonometrical, polar, and exponential function? Suppose we are having a sinusoidal function, v1 is equal to vm sin omega t plus minus theta 1, and v2 is equal to vm sin omega t plus minus theta 2. And this sinusoidal function can be written in polar form, that is vm plus minus angle of theta 1. Similarly, v2 vm 2 angle of plus minus theta 2. This quantity is vm angle of plus minus theta 1. The second quantity is vm2 angle of plus minus theta 2. The maximum value of vt and vm. If we want to write in RMS form, then Vm divided by root 2, then Vm2 is divided by root 2. These quantities can be written in RMS form as well. Here we can resolve these two components along by having a theta, then x will be along x-axis, it will be V1 cos of plus minus theta 1, similarly V2 cos of plus minus theta 2 in a phasor. Then similarly for y, along y-axis we can resolve these two components is v1 sine of plus minus theta 1 plus v2 sine of plus minus theta 2. And here resolving these two components is nothing, we can find out the sum of these two quantity v1 and v2. Although the earlier it was instantaneous form, this instantaneous form is represented in polar form, and this polar form is converted into rectangular wave or phasor in phasor form. Here we consider that there are quantity v1 and v2 within a phase displacement of theta 1 and theta 2 with respect to reference. This is nothing but real, this is imaginary axis. Along real and imaginary axis, when these two quantities are resolved, then we can find out x and y. Knowing the x and y, we can calculate the magnitude of resultant of these two quantity, and this resultant is nothing but the parallelogram. Applying parallelogram law of forces, we can also resolve this component as the resultant VR, the phasor sum of these two quantity. But here we are not finding out using the phasor, we are simply finding out using the mathematical notation or complex algebra. Now, considering this complex algebra, we can find out the magnitude of the resultant quantity if we want to add these two quantities in phasor. Then the resultant value will be somewhere in between the two. Now, this is when these two quantities are negative, theta 1 is negative, theta 2 is negative, the resultant value will be this. And if one quantity is positive, another quantity, one angle is positive, another angle is negative, then the phasor representation will be this. Now, knowing the value of VR, resultant value of VR, then the resultant phasor of these two quantity is represented using this VR resultant. This quantity will be resultant, whatever quantity we are getting from here. The theta we can calculate from here, y from y and x. The resultant theta will be this. The resultant value of Vm is this. Then knowing the magnitude and angle, this resultant, the resultant here means the phasor sum of these two quantity can be represented as Vr sine of omega plus minus theta r. Theta can be plus or minus depending upon the sign over here. Then it can be written as polar form, then it will be maximum value Vm angle of plus minus theta r. Now, considering this complex notation, here we are having a addition in complex mathematically. Either we are going to sum the quantity, or we are going to subtract or divide or multiply the quantity. In mathematical formulation, if we are considering addition, better it is considering the rectangular form. In rectangular form, we are having real component, imaginary component. For another quantity, real and imaginary component, adding real with real, imaginary with imaginary, and then we can find out the resultant quantity. Similarly, if we want to subtract two quantity, knowing the value of real and imaginary component of one quantity, similarly for another quantity, adding or subtracting real with real, imaginary with imaginary, then we can find out the resultant quantity. Whereas when we want to multiply and divide, it is better to consider a polar form or exponential form. In polar form, if we are having v1 and v2, v1 angle of theta 1, v2 angle of theta 2, then multiplication, taking the multiplication, the resultant, we just multiply this magnitude with magnitude and adding or subtracting the angles. Similarly, when we are taking the division, in case of division, considering two quantity in polar form, we are just dividing the magnitude with magnitude and taking the sign of plus and minus, as if it is in denominator it is plus, in numerator then it will become minus, and so and similarly if it is minus it will become plus, the resultant quantity will be VR, we can find out. Now these are the different four representation of AC quantity in phasor and their significance while taking a addition, multiplication, subtraction and division. And in summary, we can say addition and subtraction is usually performed in rectangular form, whereas multiplication and division is usually performed in polar form. But there is no hard and fast that we should follow this only and we should follow this only. That depends upon the method used and as well as depending upon the mathematical calculations. It makes calculation easy when it is subtraction and addition. It makes calculation easy when it is multiplication and division.